Satyabhama Institute of Science and Technology, Chennai. 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 Institute of Science and Technology, Chennai. Satyabhama 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 Institute of Science and Technology, Chennai.
Good afternoon to all. Today we are in the one. Good afternoon to all. Today we are in the fourth day of a 2 weeks international workshop on emerging trends in the field of science and technology. Once again, I welcome you all the participants, sir. Sir Sudhakar Chandran, sir.
Hello, good afternoon.
Yes, sir. You can go for check your sharing, sir. Screen sharing.
Sure. Let me share the screen so that you can see the slides. So you can see the slides.
Yes, sir. Visible, sir.
Okay, excellent.
Let us start the program exactly by 1:30, sir. You have to wait 3 more minutes.
Yeah, I'm ready. So anytime you let me know, then we will begin. Okay.
Thank you, sir. Thank you, sir.
Welcome, sir.
Hello.
Welcome, sir. Thanks for accepting
Thank
the
you.
invitation, sir.
Hope the program is going well so far.
Sir.
So the talks are all through the day you have, or only in the afternoon, or how it has been organized? I was not aware of the full schedule, so.
One session per day.
Pardon?
One session per day.
Oh, one session, is it? Okay, the session is like a 1 hour session, is it?
Yes, sir. Yes, sir.
Oh, okay.
Good afternoon, sir.
Hello, good afternoon.
Welcome, sir.
Thank you. It's my pleasure. So you need my video to be on, or?
It can be on, sir.
Okay, fine. Thank you.
Shall I start the session, sir?
Yeah, please.
Yeah. On behalf of the organizers, I stand here to offer you a very hearty welcome on the fourth day of the two-week international workshop on the emerging trends in the field of science and technology, organized by the Department of Physics, School of Science and Humanities, Satyabama Institute of Science and Technology. Let us begin today's session by seeking the blessing of the Almighty with a prayer song. Let us start the program with Bharatatai Valtu by Master Vasudevan, doing his grade 7 in PSBB. Vasudevan.
பாரத தாயை பணிந்து வணங்கும் வீரமைந்தனா பாரத தாயை பணிந்து வணங்கும் வீரமைந்தனா அர்ப்பணமாவோம் அவள் தாளினிலே தூய மலர்கள் நாம் அர்ப்பணமாவோம் அவள் தாளினிலே தூய மலர்கள் நாம் பேசுகிறோம் நாம் பல மொழியானால் வேதம் இங்கில்லை வங்கள மொழியும் இன்ப தமிழும் எங்களதென்றிடுவோம் வங்கள மொழியும் இன்ப தமிழும் எங்களதென்றிடுவோம் கவின் மலையாளம் கன்னடம் தெலுங்கு ஹிந்தியும் எங்களதே கவின் மலையாளம் கன்னடம் தெலுங்கு ஹிந்தியும் எங்களதே பாரத தாயை பணிந்து வணங்கும் வீரமைந்த நாம் அர்ப்பணமாவோம் அவள் தாளினிலே தூய மலர்கள் நாம். ஆயிரம் ஜாதிகள் நம்மில் உண்டு, ஆனால் நாம் ஒன்று. மாநிலம் பலவாய் பிரிந்திருந்தாலும் மக்கள் நாம் ஒன்று. மாநில பலவாய் பிரிந்திருந்தாலும் மக்கள் நாம் ஒன்று. வழிபடு தெய்வம் பலவானாலும் அனைவருமே ஒன்று. வழிபடு தெய்வம் பலவானாலும் அனைவருமே ஒன்று. பாரத தாயை பணிந்து வணங்கும் வீரமைந்த நாம் அர்ப்பணமாவோம் அவள் தாளினிலே தூய மலர்கள் நாம். தொழில் செய்தாலும் கல்வி கற்றாலும் தேசத்தின் நன்மைக்கே. தொழில் செய்தாலும் கல்வி கற்றாலும் தேசத்தின் நன்மைக்கே. நாட்டின் உடைமை நாமே அழித்தால் நஷ்டம் யாருக்கு? நாட்டின் உடைமையை நாமே அழித்தால் நஷ்டம் யாருக்கு? செய்தொழிலனிலே வேறுபட்டாலும் யாவும் அவள் தொழிலாள். செய்தொழிலனிலே வேறுபட்டாலும் யாவும் அவள் தொழிலாள். பாரத தாயை பணிந்து வணங்கும் வீரமைந்த நாம் அர்ப்பணமாவோம் அவள் தாளினிலே தூய மலர்கள் நாம்.
Thank you, Vasudevan. Today, on the fourth day of the workshop, we have with us Dr. Sudha Chandar of IITM. Welcome, sir.
Thank you.
To say a few words about our speaker, Dr. Sudha Chandar is currently the professor in the Department of Physics, IIT Madras, India. He has served as a visiting guest researcher under Carl Trigger Postdoctoral Fellowship in Royal Institute of Technology, Sweden, in the period 2004 to 5. He also served as a research professor, Department of Physics and Astronomy, Wayne State University, USA, during the period 2009 to 10. He was awarded with DAD Fellowship, RWTH, Akron University, and Ruska Research Center during 2013. His research interest includes defect engineering of multifunctional materials, focusing on controlling the growth and properties of wide range of thin films, nanostructures, complex heterostructures, and 2D materials, characterizing these structures and compositional properties by wide range of techniques with special focus on HRTEM and spectroscopic techniques such as XPS, Raman, UV, IR to understand the defect structure properly, correlations of multifunctional materials. His group also focuses in semiconducting oxides, multiferrox, nanostructured magnetic materials for sensor applications, transition metal, chalcogenides, and nanostructured oxides for energy conversion applications, with current focus on magnetic and multiferroric materials, materials for semiconducting, peroxide and quantum dot sensite solar cells, and developing cathode and anode materials for lithium-ion battery applications, etc. He has collaborated with many researchers from Germany, USA, South Korea, and with leading companies including NISA in developing materials with high performance for battery applications. He has graduated 6 PhD students, mentored 5 postdoctoral fellows, and currently his group comprises of 8 scholars pursuing research in wide range of materials for energy storage, energy conversion, and sensor application. He, with other colleagues at IITM, has proposed to bring up a center for advanced material and microscopy with the aim to solve the challenging materials properties using atomic scale microscopic techniques and spectroscopy methods. He has received grants from various funding agencies. To mention a few, 99.5 lakhs grant from MHRD STARS during 2020-23, 2.21 lakhs from MHRD grant during 2021-22, and a grant of 1.65 crores from DST materials for energy storage during the period 17 to 20, and 1.66 crores from DST Solar Energy Research Institute during the period 2013 to 16, and many. To say a few honors, he had been repeatedly getting Bhagya Lakshmi and Krishna Iyengar Award for guiding PhD students for innovative projects in energy. Consequently, for the continuously for 3 years, 2017, 18, and 19, and he has received many fellowships. Okay, to add up to his scientific excellence, he has researched in on multifunctional materials for energy and sensors and has resulted in more than 125 peer-reviewed articles with more than 3,600 citations. His H-index is 35 and I-10 index is 79, with an average citation publication per site is 22. His research articles are published in reputed journals such as ACS, Interface Materials and Interface, Applied Physical Letters, top journals in IOP, ACS, RSC, Elsevier, etc. With this introduction, I invite our today's speaker. It's an honor to have such an eminent person like you, sir, in this platform. Welcome, sir. And here he is to enlighten us with the scope and potential of defect engineering of functional materials for improved energy conservation and energy storage applications. Welcome, sir.
Yeah, thank you. Thank you for the nice introduction.
Sorry, sir, if I missed something.
Oh, no problem. I think you read pretty much my CV. Sorry, that much is not required. So anyway, thank you very much for introducing me to the audience. So can I get started with the presentation?
Yes, sir.
Okay, thank you. Thank you one and all for being here to listen to this talk. I hope I am audible to all of you. If not, please let me know. And also you can interrupt me at any point during my presentation if you have any doubts. If you have any questions to ask, please stop me, okay? So today I plan to do this talk on defect engineering in functional materials. Basically, many of the materials are being explored for energy conversion and energy storage applications. Obviously, in this world right now where we are using energies like in an exponential way of increase, we need to find alternative resources because the current resources would get exhausted at some point, and also they are not green. So a lot of pollution and other things happen. Therefore, in order to prevent all this, and we need to find alternative methods of getting the energy, and also we need methods to store them and use it whenever we need to. So that's pretty much the goal. But then there are various methods are being explored where whatever you do, you need materials to address these aspects. Okay, so in this particular talk, I'm going to emphasize on how the defects in the materials can can be used to augment certain properties, and that will eventually increase certain performances of the materials, both in the energy conversion and energy storage application. Okay, so before I go, let me introduce about my research interest in my group. I run a group which is called Multifunctional Materials Laboratory in the Department of Physics, IIT Madras, which basically looks at the defect structure property correlations in oxides. Not necessarily oxides, we do work on chalcogenides and halides, mainly focused on applications like magnetic materials, multiferroics. In the last 1 decade, I have also started working on um, the materials for battery applications and also materials for solar cell. Basically, we look at the structural aspects and then tailor them so that the functional properties can be enhanced. And in the process, we specifically focus on the defects, engineering defects. There are lots of applications. If you take oxides, no, there are lots of applications. For example, if you take BiFeO3, it's a multiferroic material. It exhibits very interesting property where the coupling exists between the ferroic and ferroic order parameters, like the magnetic property and the ferroelectric property. There is a correlation, and you can control one using the other. And these kind of materials are very much useful for spintronic and magneto-optoelectronic devices. But there are a lot of challenges. Such devices are not effectively realized. So there are a lot of research is going on. So we also focus on understanding them from the materials perspective, how one can address in order to realize these functional properties. Of course, we do work on oxides for lithium-ion battery applications. Both anodes and cathodes are being explored. In today's talk, I will touch upon the molybdisulfides, nano sheets of molybdisulfide, how it behaves when it is made up of different extent of the defect concentration. In my first part of the talk, I will touch upon the BiFeO3 material properties and how it can be useful for all solid state solar cell as an all solid state solar cell device. Okay, we do work on various other oxides and perovskites, halide, inorganic, organic, and halide perovskites for specifically on solar cell application. In the context of solar cell application that I would touch upon using BiFeO3, I will also give a glimpse of what we have come up with, a new kind of solar cell we call vispronic solar cell. So I'll just give a brief about it. So with that, let me, I have this following outline at the top. First, I will give a brief introduction to the defects in oxides, because we need to understand how the defects, what are the defects, and what kind of defects that I'm going to describe in these two examples that I'm going to discuss today influences the properties. Okay, so let me first begin with a very generic introduction to the structural defects in metal oxides. What the picture you see is basically comprised of red spheres and black spheres. Okay, so the red is basically anion and the black is a cation. For example, in such an ordered structure, the black sphere can be missing. We call that cation vacancy. Or a red sphere can miss. We call anion vacancy. These are all basically like NaCl structure is something you can think of, Na plus and Cl minus. If sodium misses in the lattice, then we call this cation vacancy, and chlorine is missing, then we call it anion vacancy. Of course, in place of sodium and chlorine, some other atom can sit. We call them substitutional dopants. So dopants are also a kind of a defect that exists in the structure. It could be intentional or it could be unintentional one. So impurity dopants are unintentional ones. You may not want it, but somehow you could have got there. But it influences the properties very much, and it is very important to understand how it influences. Okay, so we can have a dopant vacancy pair also. For example, the substitution dopant along with the missing of anion or cation can also be there. Or these dopants can sit in the interstitial regions. Okay, so in between these anion and cation, you have gaps, and they can fill up those gaps and produce little strain. Somehow, like if there is a in a school bench, if there are 3 students are supposed to sit, we try to squeeze 5 of us in the same bench, right? So somehow we accommodate. So also the lattice accommodates extra atoms in between in these interstitial sites. Sometimes the vacancies and along with the whatever the cation or anion vacancies can order in a structural ordered fashion. Therefore, it produces a vacancy ordering. It sometimes it could be localized, or sometimes it could be everywhere. Therefore, it becomes a new phase. In addition to these, you do have dislocations and various other line defects, planar defects, and so on. So all of this, the concentration of this in a given crystal structure is going to affect the properties. Of course, this is the schematic what I showed. Let me give a real pictures. So here is an example for the point defect. So for example, these are all high resolution images of some of the oxides. So you can see that it is supposed to be a perfect cube, but then there are certain distortions that you can see. In this place you can see, and here you can see. So either they are stretched out or there is some kind of strain present because of the missing of atoms. In this case, it's the oxygen vacancies are missing in indium oxide matrix. Therefore, you can see locally, the missing atom introduces a lot of strain in the lattice. So there are also other kinds of defects that could come, linear and planar defects or dislocations, like the ones which is shown here, or some other material can get included in the lattice. Therefore, bulk volume defects are there. You cannot avoid the surface. Surface introduces lots of, it influences the properties a lot, because in nanoparticle, the surface is a large chunk of component. You cannot ignore it. So as you see in this picture, the surface is very much disordered compared to the core. Core is very crystalline. You can see the lattice planes, well-ordered lattice planes, but the surface is pretty much disordered. Therefore, a surface, interface, and grain boundaries play a very important role in controlling the properties. Okay, so with that, let me get into this first topic of bismuth iron oxide. Okay, I'm going to say, I will tell about certain properties, how do we control, specifically the band gap of this material. And then I'm going to give an application of that in the solar cell, which is an energy conversion device. BiFeO3 is a perovskite structure, like AbO3 structure, but it's not a perfect cube. The one which is shown is a perfect cube, but it's not perfect cube because the octahedra, the FeO6 octahedra, is slightly distorted and tilted, and therefore it does not form a perfect perfect perovskite structure, and therefore it forms a rhombohedral structure. So it's a distorted rhombohedra is what the perovskites, the BiFeO3 structure is. It has, because of this, it exhibits very interesting properties. The displacement of the cations and anions means, it gets polarized. The polarization it leads to long range order. So it's along the 1-1-1 direction of this particular structure. You also have a magnetic properties, which I'm not going to discuss, though we have done very extensive work on magnetic properties of these materials. So of course, this particular material is very interesting, because if you look at the large class of insulating oxides you might have come across, the insulating oxides can be, some of them could be electrically polarizable, some of them could be magnetically polarizable, so like the ones which is shown in these green and orange circles. But some of them could be ferroelectric, and some of them could be ferromagnetic, so as shown by these red and green inner circles. But there are very few materials like the one here shown, bismuth ferrite and terbium manganite, and BiMnO3 and so on. They are both ferromagnetic and ferroelectric, very few, and also they exhibit multiferrite properties. So the compounds that exhibit both magnetoelectric and multiferrite compounds are very, very few. But then in this particular talk, I'm not going to discuss the magnetoelectric properties or multiferrite properties of this material, but I will show how the same material can be used for solar cell application. It's important to understand the defects that would exist in these material. For example, you have a valence band and conduction band. It's an insulator, roughly about 2.8 electron volt band gap. Oxygen vacancies are pretty common in this structure. So specifically, when you prepare the materials in the oxygen poor conditions, you would end up with oxygen vacancies that lie pretty close to the conduction band. It could be neutral or charged state, but mostly in our studies we found it's a neutral state. And of course, you can also have a cationic vacancies like I showed in the first picture, where the vacancy of bismuth and vacancy of iron reside close to the valence band. They are acceptor dopants. So depending on the concentration of what kind of defects you have, the properties would change a lot. In any case, the states that are pretty close to the conduction band or valence band, the donor and acceptor states, they can contribute to the overall conduction with a little energy, and therefore it's going to modify the electrical properties of the material a lot. Of course, those states which lie deep might affect the properties as well by trapping the charge carriers, but we may not come across that in our case much. But whenever the oxygen vacancies do exist in this particular structure, it can be seen that the oxygen vacancy related defect states are mainly localized close to the iron sites rather than the bismuth sites. So these are the two, the charge density, distribution of charge density due to the oxygen vacancies are shown from this particular paper by Clark and Robertson, which clearly demonstrate that the energy level, how the vacancy related energy level, where do they reside, and therefore how it can influence the properties. Okay, in addition to what I discussed, the defects, how it can have influence on the electronic structure and so on, we can have other kinds of defects which basically introduce lots of lattice strain, specifically in the nano materials. So this particular picture, of course, taken from this reference, you can see that depending on the size, the surface atoms are relaxed. They introduce they don't have any more atom to bond from the outside. Therefore, the energy has to be relaxed, and it puts a lot of strain within the crystal, and this is what we call the microstrain. And this microstrain can come because of the size or shape effect, and it can also come because of the alloying, okay, or what kind of core shell structure you have, and lots of other things you can contribute for this kind of microstrain. And in fact, I'm going to show in the BiFeO3 example that the microstrain we kind of estimated on BiFeO3 nanoparticles, in fact, influences the optical properties a lot. So let me also emphasize that if you want to study the defect structures, you have to use a different set of tools to identify them. We use the high resolution TEM as one of the tool, and also we understand the local structures using spectroscopic techniques like Raman, XPS, and so on. So I will give few examples as I move on this on this particular example, BiFeO3. Okay, so let me first begin with this role of microstrain and oxygen defects, what it does to the BiFeO3 structure. So we prepared BiFeO3 with the different sizes. For example, the size of the crystals are shown here. As you can see, as the size increases, at very low, smaller size, it's more kind of amorphous, but they are crystalline, as I can show you from the TEM picture. As the size increases, you can see that these doublet peak, which is basically the one of the 200 peak in a cubic perovskite perfect cubic structure, splits up. Of course, this split up peak in fact moves in opposite direction. Or in other words, if you go down in the size, they try to come together, which means the distortion is going away as you decrease the size. And that's what we found. The micro strain, as you decrease the size, increases to especially around 30 nanometer a lot. And at the same time, you see the lattice parameters also change a lot, especially specifically C by A ratio. So the micro strain that comes from because of the size effect has an influence on the structure. Here is the example of the 5 nanometer crystals we had. Of course, there's a large component which is amorphous. But as you increase the size from 5 nanometer to 22, these are all average size that I have pointed out, and 38 and 65 nanometer, more and more larger, well-ordered crystallites are obtained. But then specifically around the crystal size of 20 to 30 nanometer, we do observe a lot of local strains. You can see that in the fast Fourier transform image that we obtained from this high resolution TM image, there are lattice planes that are pulled apart, and the same set of lattice planes in some other region are pushed. They are all pushed close to each other. So there is a tensile and compressive strains within the lattice, and of course, these kind of strains go away as you go to very large sizes like 65 nanometer. And this has an influence on the optical properties, specifically the band gap structure that we have studied shows that around 20-30 nanometer, there is a sudden decrease in the band gap value. And this, which means, we can control the band gap by tailoring these defects. That's what the message we get from this very set of first set of studies that we did in the very early stage. This is the work which we published long back in Applied Physics Letters. But then what is the implication of this controlling the band gap means? For example, the bulk materials of BAFUO3 have a band gap of around 2.78 electron volt. Now, by going to the smaller size, I'm able to decrease it further to close to 2, and maybe much closer to 1.5 EV, which is a typical band gap value of a material that is required for its use, efficient use as a solar cell material. Okay. Of course, silicon is the most commonly used solar cell material. There are cadmium, telluride, and other materials, but many other are being explored. But then we need stable and energy conversion efficiency should be fantastic in the materials that we explore, and that's been the challenge. And of course, there are different kinds of solar cells that have come up. I will discuss some in the later part. Okay. So in this particular example I gave, the strain which comes because of the size. As you reduce the size, the oxygen vacancies which reside on the surface of the nanoparticles changes the properties. We can do the local strain can also be included in these lattice by introducing allovalent cations, like instead of bismuth, you substitute some other similar ionic size cation, but with a lower oxidation state, which would introduce oxygen vacancies. So for example, here the oxygen vacancies are introduced because of the substitution of a different atom than the bismuth, as shown by the colors. So we did this calcium dope BaFuO3, and then of course calcium doping itself introduces a lot of complex changes in the structure, and it's also temperature dependent, the temperature of the annealing. Okay, so as you can see, the lots of dots, will order the dots in these diffraction images you can see, like the one shown, and these all indicate that the oxygen vacancy is in fact order in this structure. So here is the one very interesting ordering that we found. It is almost like 36 angstrom repeat order. In another case, we got 64 angstrom. 4 angstrom is the typical, around 4 angstrom is the lattice size of the BiFeO3. Now this becomes much larger because of the presence of oxygen vacancies. So oxygen vacancies, in fact, can be inferred from this kind of ordering that exists in these structures. In pure case, you do have defects on the surface, as has been pointed out here. But in the calcium dope cases where oxygen vacancies get introduced even within the crystal lattice, the core of the crystals, you can see a lot of distortions coming up. One can also minimize that by co-substituting titanium at ion. Okay, so bismuth 3 plus and calcium 2 plus, the one charge difference is compensated by Fe3 plus and titanium 4 plus. So equimolar substitution of calcium and titanium seems to get rid of the core defect states, but again the surface defect states are prevailing, and the titanium doping also introduces the size reduction. Okay, so now what we did, of course, I don't want to go through all this thing, but I would like to emphasize on one particular aspect. Since the size gets modified because of the dopant, and also the electronic structure is changing, there's a lot of competing factors that control the band gap. But what we found, the band gap can be brought close to 1.2 electron volt in the particle size ranging from 0 to 70 or something. But in some cases, we could go down to 6 voltage, but this requires very high temperature, specifically in the calcium dope samples. But in any case, we could control the band gap all the way from 2.4 EV to 1.5 EV in these materials. Of course, the very low band gap materials are high temperature process. Therefore, there is a challenge in designing the device for solar cell. So we have chosen an optimized band gap that we can lowest size that we can get, and we tested the photovoltaic properties. So the photovoltaic cell that you would make would be all solid state in this case, because the BiFeO3 is known to show very large open circuit voltage, and for example, the domain walls are shown to play a important role in getting very high open circuit voltage, because this particular solar cell works in a different way than the silicon solar cell works. In silicon solar cell, the inbuilt potential comes from uh, the diffusion region, right? So the PN junction region, whereas in this case, the domain walls introduces local inbuilt region. It's like tiny electrostatic potential steps at the nanoscale ferroelectric domain regions, and these act as inbuilt potential. And when you have large number of such domain walls, the tiny inbuilt potential, they all add up, and therefore a large open circuit voltage as high as several tens of volt can be achieved by this particular design. So we were interested in this aspect, and therefore explored the photoconductivity properties, and the photoconductivity properties of these calcium and titanium doped BiFeO3 is very promising, and we have done extensive study on this compounds. I will just tell the gist of it. So basically, the defects that would reside mostly on the grain boundary regions, and also that comes from the calcium and the titanium doping seems to play a very important role uh, in, uh, uh, in in deciding the photoconductivity. For example, 3 to 4 orders of increase in photoconductivity can be obtained just by changing the composition. And of course, there is a different mechanism. The mechanism could be could be summarized into two different parts. The one that comes from the grain boundary region, where the defects are prevalent, and also from the bulk region, where the dopants, depending on the dopants, the type of dopants you introduce, oxygen vacancies could come. One can also tailor these by just annealing them, and that's what I have shown here. If the same set of samples, if you anneal them in air, and the grain boundary conduction is shut off, therefore there's a significant reduction in the photoconductivity. How do we understand this? Of course, the defect states mostly in the pure bismuth ferrite. There is a large band gap, something like anywhere from 2.4 to 2.8 eV, which is consistent with what we find from the experimental. But in the case of samples that have surface defects, you do have energy corresponding to the oxygen vacancies from the surface region or due to the dopants, and these depending on the concentration, they can make a separate energy bands, and therefore the optical properties do change, and then the band gap do change, and therefore these oxygen vacancies are known to play a significant role in controlling the photoconductivity properties. So we made very simple devices. These devices, unlike the sensitized solar cells that I will discuss in some time now, are very different. They are all solid state. You have a glass substrate on which FTO is coated. It's a fluorine doped tin oxides. And on top of that, we make BiFeO through thin films, and then gold contacts are given. And therefore, you can shine the light either from this side or from the back side, and then find out the current generated, the whole current and voltage characteristics of the device. So these devices we tested also exhibit similar photoconductivity response that we found in bulk samples. More interestingly, as I mentioned at the beginning, the bismuth ferrite is both ferroelectric and ferromagnetic. The ferroelectric property can be seen from the ferroelectric loop we have measured on these thin films. And you can also show that by polarizing and switching the polarization, you can change the ferroelectric nature of the particles. Okay, so here is the example. A small region is chosen, and you put a high negative voltage bias, and then you orient the ferroelectric domains in one particular direction, and the other part, you can switch it by applying positive this one. So what happens when you do, because of this ferroelectric nature, as I explained earlier, the domains play an important role in the inbuilt potential, and therefore large open circuit voltage can be inferred, and that's what we see here in the pristine BiFeO, three thin films, up to 3 volt we got, but then the short circuit current is very, very small, which is typically, 0.1 microamp, which is very, very small. We need very large short circuit current in order to get very good efficiency. So we tested the devices made using calcium and titanium. The calcium, as I mentioned, it introduces lots of oxygen vacancies. The moment oxygen vacancies come, the ferroelectric nature goes down, and therefore the inbuilt potential is kind of gone, and you see that the inbuilt potential due to the ferroelectric domains are gone, and you see only the inbuilt potential due to the contacts come into picture, and therefore the open circuit voltage decreases. But then we found a large large short circuit current, which is a good thing. So the defects increase the short circuit current, but then kills the open circuit voltage. By doing both calcium and titanium, we could retain both of it. That was the beautiful study that we showed, and we did large number of device testing, and we found that the efficiency in an optimized condition can be attained close to 0.2%. Remember, these are all the thin films, polycrystalline thin films, done by very simple process like a spin coating. but then we do get efficiencies close to 0.2%, which is very high, and that kind of high efficiency is not reported on this particular material. And also, as you can see from in this particular picture, if you want to get high open circuit voltage, you should have a ferroelectric nature, and that's what this blue color shading shows. If you want a high short circuit current, you should have a large oxygen vacancies, and that's the green current show. So both are in the two different direction. So you need to find an optimized condition, because if I keep on increasing the oxygen vacancy beyond certain point, it goes that side. You can't go here. That would have been very ideal. If I would have pushed this particular thing beyond this region somewhere, then it would have been fantastic. But anyhow, we are trying to work on other materials where we can push it a little bit further, or some of the composite system that we would like to explore. And in any case, the defects present in BiFeO3 structure is shown to alter the solar cell properties very significantly. We do work on other perovskite structures. Specifically, you might have come across the perovskites, the inorganic, organic halide perovskites, and all inorganic perovskites. Specifically, the double perovskites are of interest because they are more stable compared to any of the single perovskites, single halide perovskites, or inorganic, organic halide perovskites. We found one of the very interesting observation in this particular double perovskite structure. The double perovskite is something similar to single perovskite. Only thing is, there are two different cations, like in this case, silver and bismuth, and they are they order in a ordered fashion, in a alternate way. Therefore, the perovskite unit cell becomes almost double. Okay, and in this particular case, we substituted sodium in place of silver, and the structural changes are as usual. It's very linear change, so there is nothing unusual. But then when we measure the band gap of these materials, then we found this does not vary in a linear fashion, and there is a nonlinear way, we see. And you can fit this curve to some extent using the Bowing, using a Bowing parameter. But then when we try to understand why such a deviation is seen, we using Raman spectroscopy, we found a very simple thing, very interesting thing, that the sublattice distortion is the reason for such a deviation in the band gap. So what is sublattice distortion? Basically, this BiCl6 octahedra. In this case, this purple color octahedra, and then the green color octahedra. Depending on the green color octahedra is to begin with silver when Na is 0. There is a lot of these two, because of the bonding characteristic, these two they don't go well. There is a lot of mismatch in the octahedra. And the moment you substitute sodium, that mismatch goes away slowly, but then it does not happen in a linear fashion. And as you can see from the Raman spectroscopic studies, how the peak shifts, how the peak broaden, these are all these peaks, the shift in the peak positions and things all show how the octahedral properties, octahedral structural features change. And you can see that around 60-70%, there is a sharp change, and that's the same region. You also find the band gap changes very sharply. And this implies that the oxygen sublattice distortion that gets that we can manipulate by sodium substitution in this double perovskites is very important, and therefore it controls the it controls the band gap. In fact, depending on the Bowing parameter, there are examples, but not in this double perovskite, where it can go in the negative direction as well. So like this. So if you find a double perovskite which can do this, then you can push the band gap to lower value. Of course, if you choose a n-member compounds pretty close to 2 eV or something, realizing 1.5 to 1.8 eV is very much possible. And therefore, this kind of material, which are very stable, will be useful for solar cell application. Anyhow, we are working along this line currently. Let me introduce you to a sensitized solar cell. The sensitized solar cell is a is a well-known um, device structure. It's also known as Gratzel type solar cell. It's known from 1990s. This kind of cell has a transparent conducting layer, and on which TiO2 nanoparticle porous mesoporous layer is coated, and then you can sensitize them with dye or quantum dot or thin film. And therefore, what happens when the light falls, the dyes, which has either has a homolumo gap or quantum dots, which has a valence band conduction band, which can be tuned. The light gets absorbed, the electron goes to the excited state, and these electrons are grabbed by the TiO2, and therefore, the current flows in the external circuit. Of course, you need to regenerate the dye, and there is an electrolyte involved in it. Mostly, this electrolyte is liquid. You do have some of the organic electrolytes, which are jelly or some other format. So various inorganic and organic electrolytes are also being investigated. So electrolyte research itself is very in-depth one. So in this particular case, what we found, of course, there is a lot of time scale involved. So most of the time, as you can see, this particular process is the excitation process, and then the electron going to the TiO2. They all in the picosecond scale, and of course, the electron which goes to the TiO2 can get recombined with the dye itself, de-exciting it. So such recombination are not going to yield a very effective solar cell device. So we need to prevent these recombinations, the electrons that we remove from this process, but then not effectively taken out of the circuit. They can get recombined. So a lot of strategies people use to improve the solar cell properties of this kind. The dye sensitized solar cell is the most commonly explored one, but quantum dot sensitized solar cell are also explored. So in order to effectively remove the electrons, you need to have a good connection between the nanoparticles, or people have explored one-dimensional structures. But then the light is also not getting scattered or effectively used. So people use different kind of scattering layers. Lots of approaches are used. But what we found in our very preliminary studies earlier, we found that the oxygen vacancies, in fact, that is present to a different extent in various nanostructures, affect the solar cell efficiency. Okay, so like we have tested nanotubes of TiO2, and then these kind of hierarchical nano bundles or random porous structure, the tubes made by Sol-Gel process, and so on. So in all these structures, the efficiency of the solar cell varies to a large extent. And we found out that whenever the oxygen vacancies are large, the efficiency goes down. But then um, the efficient way of electron transfer does happen in that material, but then the efficiency goes down because they are not effectively taken out. So in that process, what we did, we came across this particular structure where TiO2 micron size spheres. You can see that the scale is 5 micron here. So they are typically anywhere from 1 to 5 micron size, micrometer size, and these kind of micron size spheres do exhibit very sharp peaks when you take the PL, and these are nothing but the whispering gallery modes. So whispering gallery modes are nothing but for example, you might have been to Golgombas or St. Paul Cathedral, where if you speak in one place, just, if you whisper in one place, somebody from far on the other side will be able to listen you, but not in all places, only in certain places. Okay, so this kind of structures, many of them are there in our own country. The Golgambas is one example. And this is the acoustic whispering gallery. So what happens is the sound wave that you send, it gets reflected from the walls, and they circulate and establish a resonance. And wherever the amplitude is maximum, you do hear the whispers. The other places you may not hear. The optical version of this particular one is the optical whispering gallery. Of course, sound waves are larger, so you need structures of several tens of meter, whereas light waves, the lambda is very, very small. It's 500, anywhere from 400 to 700 nanometer. So you need a visible light. You need micron sized structures, and the spheres serve the purpose. So when the light gets total internal reflected inside the sphere, they get trapped and they circulate around, establish a resonance, and therefore you get very intense scattering. Of course, it doesn't get trapped forever, because the micron size spheres we do have are not perfect. You can see there are lots of surface cracks or things are there, and therefore they eventually get emitted. When they get emitted, you see lots of these modes, and these modes are called whispering gallery modes, resonant modes. And in our structure, what we did, we used these micron size spheres in combination with the mesoporous TiO2, and therefore, the micron size spheres can produce whispering gallery modes, whereas the mesoporous TiO2 provides a conducting pathway. And so like the one I show here, this is a sphere and nanoparticles are present on the surface, coated. So this is the typical structure you will see. In such case, we found that the efficiency can be increased by several folds. And this is one of the data from the cadmium selenide quantum dot sensitized Vispronic solar cell. So we used cadmium selenide quantum dots, and without such a the micron size spheres, we get something around 1.6, less than 1.5 percent efficiency, whereas it can go to 2.5% the moment we introduce these whispering gallery mode exhibiting micron size spheres. Of course, these the whispering gallery modes that come from the spheres, they strongly couple with the quantum dots, and therefore the increase is because of that. In fact, we have tested various sensitized solar cells. This one is N719 dye. This is a typical dye sensitized solar cell, the Gratzel type. And then we have tested copper indium disulfide quantum dots. We also made thin films of copper indium disulfide on these spheres. So all of them, they show a large extent in the efficiency. And we call this particular modified Gratzel type solar cell and Vispronic solar cell, because the whispering gallery mode helps in enhancing the efficiency a lot. Okay, so with that, let me move on to the second part, where I will quickly summarize the moly disulfide nanoshades, how the high rate capability can be tailored, which is a very efficient, which will be an efficient anode for lithium-ion battery application. Okay, so to give a brief introduction about moly disulfide, in fact, if you know the history of batteries, moly disulfide was at some point explored for lithium-ion battery very long back, 1970s. The Moly Energy company, in fact, came up. Professor Whittingham is the one who explored, and of course, he got the Nobel Prize for designing the lithium-ion batteries. The lithium-ion batteries do have cathodes and anodes. Generally, anodes are graphite. Cathodes are oxides like lead oxides or LiFePO4 and so on. See, the open circuit voltage basically comes because of the Fermi level difference in the Fermi level between these, and it can be changed as you charge and discharge, basically as you push the lithium in and out of these structures. The challenge is, the lithium-ion batteries, they work very well. For example, right now on my computer, because I require very small power, and as long as I draw very small power, it can deliver maximum specific energy. But then if I need to draw a large power, if I want large specific power, the amount of energy that I can get out of the battery drastically goes down. Okay, which means, I cannot use these batteries in vehicles. If I want to start the vehicle, I need to draw a large power, and that's not possible. Therefore the batteries literally fail. And therefore the challenge is now to make batteries which can deliver with a large specific power and so on. uh, Drawing large current basically means, we provide a term called current rate, which is nothing but, for example, if you know what is the charge capacity of your lithium ion battery in your mobile phones, you might have come across when you buy a mobile phone that it may be 6,000 milliampere hour, which means, that is the capacity, that's the capacity, so much of charge is stored. And I can draw all these charge either in a minute, or in 1 hour, or in 10 hours, and so on. So if I do it in 1 hour, I call this 1 C rate. C by 1 is 1 C rate. If I draw that in 10 hours, C by 10, which is 0.1 C rate. Okay. If I draw that in kind of a half an hour, then uh, it is 2 C rate. I can draw in much smaller time, right? So then I can go 10 C, 20 C, and so on. So larger the C rate, which means, you are drawing the current at a much faster rate. And in fact, you need materials that can withstand you can build the lithium ion batteries out of these materials, which can withstand large current drawn in a short time. Okay. So graphite, in fact, does not support that particular. Graphite is the typical anode that is used in the lithium-ion batteries. It does not support, and therefore people are exploring various other materials, and also the capacity of the graphitic or carbon-based anodes are somewhere around 350 milliampere hour per gram. But for example, moly disulfide exhibits much higher capacity. But only problem is, as you keep on cycling, it goes down, and there is a structural change, and therefore one needs to understand how one can tailor it to make it suitable for lithium-ion battery application. So here is a typical structure of moly disulfide. It's a layered structure. In each layer, you have one molybdenum layer and 2 sulfur layers, and these are all stacked and held by van der Waals force. Okay, so there are various forms of it, like 2H, 3R, and 1T phase. I don't go into the details of the structural aspects, but most of the moly disulfide that we studied are 2H form. So the 2H form basically, hexagonal stacking, ABC stacking. Like if you take a moly, the AB stacking is what the hexagonal stacking. On the other hand, if you have A, B, C, then that's the the 3R form. Okay. Okay, so we prepared these moly disulfide using hydrothermal process. As you can see here, depending on the annealing temperature, the moly sulfide nanosheet looks very different. In fact, if you can see here in the high resolution image, very few layers of moly disulfide. So each line you see here is nothing but this one layer of this. Okay, so each of these layers, they are a bit disordered, they are curved, they have lots of defects, and these defects minimize as you grow, as you anneal them at a large annealing temperature, and the number of layers also grow. Okay, so therefore in one way, we can control the defect and number of layers in these oxides. For example, here the one set of study there we showed 800 degrees Celsius for 1 hour. You do have these bending defects, and then there are edge defects. Uh, they curve actually in the curved region. There's a lot of strain present. Okay, and there are planar defects, and then the layers get torn off. So lots of various kinds of defects exist, and these defects minimize as you increase the temperature. Okay, so for example, here too, the torn part of the moly disulfide nanosheets can be seen, but slowly these get annealed out, and then they become more and more straight crystals. Only defects that you will see is from the edges where the planes terminate. You cannot completely get rid of these surface defects anyhow. So you can also estimate the edge terminations, dislocations, other folding, bending defects. For example, if you take 500-degree anneal sample and 900-degree anneal sample, you can see that there is almost like 5 to 10 times of difference in the these defects between these two samples. By annealing, by controlling the annealing condition, you can to a large extent you can control these defects. Therefore, here is an example of the strain that would present in these layers, not in the perpendicular sheet direction, not in this plane. It's perpendicular to this we have taken, and you can see that the strain is very much present in moly disulfide prepared at 500 degrees Celsius, whereas in 900 it's very less. So the moly disulfide nanosheet with a different extent of defects can be prepared. And here is the studies we did in the initial, where 800 1 hour, 5 hour, and 900 1 hour samples were tested. And as you can see in the very first cycle, large capacity can be seen, 250, 260 milliampere hour per gram for the low temperature annealed one, whereas high temperature is much lower. And in fact, in this particular study, we did the cycling between 1 volt and 3 volt in order to not to collapse the nanosheet structure. If you go below 1 volt, beyond this, your capacity will be high, but then the moly disulfide nanosheet structure will collapse. It would decompose into moly and sulfur. So it would just and then it becomes kind of a lithium sulfide battery. Okay, so in this particular case, what we found that the 800 degrees Celsius 1 hour sample exhibits a large C rate. For example, you can do cycle at 40 C rates. Even at 20 C rate, a large chunk of capacity we could see, which means the nanosheets can be used for a high C rate application. But of course, the temperature has an effect. If you have too much of ordering, it also helps to some extent having the high rate capability. But we found that an optimum condition of both the presence of defects as well as the crystalline nature is important, because each one of them support the rate. One supports the rate capability, the other supports the cyclability, and therefore you need to have an optimized condition in order to get the best of the electrochemical properties. Of course, the reason for the increase in the rate capability can be understood from this particular simple mechanism that we proposed. So wherever the defects are large, and of course we found here large lithium intake is taken in the beginning, so that's what happens. X as high as 1.6, even sometimes 1, 2 we have found it takes up, but then after that the cycling is roughly about 1 lithium back and forth. So the extra lithium that goes in is sitting somewhere at the defect sites, and it helps to make the lithium diffuse much easily. So in presence of defects, lithium diffusion becomes much easier, whereas that is not the case in the case of defect suppressed moly disulfide, and therefore the electrochemical properties gets enhanced. We did analyze the extreme compounds where a large concentration of defects is there in 500 degree anneal samples and 900 degree anneal samples, and you can see the drastic difference. 500 is not good, but then it is good in terms of cyclic stability, because initially it has a very low lithium intake when measured at 10 C rate, and then slowly it picks up which means, as you keep on cycling, its structural reorganization is happening, and therefore it makes more lithium to take part in the electrochemical reaction. And so, of course, a very detailed study we did. The very complicated and intricate reorganization of molybdisulfide during the cycling is what makes the lithium capacity to keep on changing. And therefore, these particular set of studies that we did systematically on wide range of annealed samples, with a different extent of defects, shows that, in fact, one can control the cyclic stability as well as the rate capability. Okay. Yeah. So the basic thing is, the extra lithium that gets scrapped at the defect sites are the ones that help in easy diffusion of the lithium, and in especially in the defect rich samples, right? The cyclic stability is much better, whereas in the defect suppressed sample, the rate capability is much better. So we need to have an optimized condition in order to get the best of both, and that's where around 800-degree annealed samples are pretty good. And you can go through these papers if you want more details on this. Yeah, so just to summarize, these defect-rich monodisulfide, in fact, gives a very high specific energy density and specific power density. But the challenge is, as I showed, the cycling we did between 1 volt and 3 volt is it gives only a maximum capacity of 150 milliampere hour per gram. The carbon is 350 milliampere hour per gram. We did study, in fact, we did study these electrochemical properties by going below 1 volt all the way to close to zero, and that I did not present. In fact, we have also shown that, the defects present in the initial stages, in fact, affect the large capacity that one can derive from that particular the extended voltage cycling. So with that, I think I have conveyed that, the role of defects, how it can change the structural properties, and therefore the electronic properties of the materials, and therefore how we can make use of it to tailor the functional properties of materials, whether it is energy storage, energy conversion, or other functional materials that we study, which I did not discuss today, like magnetic and multiferric properties. It seems to play a very significant role in controlling the properties. With that message, let me thank you for listening quietly. And if you have any questions, um, please let me know. I will be happy to answer. And I thank the organizers for inviting me and making you, establishing the interface between you and me, so that, I can exchange our results, and we can in fact interact and get to know a lot of things, new things. Thank you all.
Thank you, sir. Thank you. Yeah. Thanks for given us excellent talk today, sir. Thank you, sir.
Thank
Sir,
you.
we have some questions regarding your talk. Can I show it now?
Yeah, yes.
Yes. Thank you, sir.
So should I exit this, or
Yes, I'll exit, sir. Okay, is it visible, sir?
yes.
Yes. 1 minute. Yes. Yes. This is what the questions.
So the lattice train, how one can create or control, and that that was how to affect the structure, if they have any possibilities in nature. See, the lattice train, as I explained in the very beginning. Should I share the slides, or?
Yes, yes.
So the lattice strain, as I showed here, it can be controlled by various methods. Okay, in our case, we did by oxygen vacancy, as I showed here in one of the example like this. So a perfect large infinite crystal will not have any oxygen vacancies, therefore it's all perfect. But then if you reduce the size, oxygen vacancies from the surface come into picture, and therefore there is a lot of push pulling because of the termination of the bonds, and undersaturated bond can make the strain to permeate to the center of the core, and this is more predominant in the nanoparticle size. But in the bulk samples, you can do this by introducing oxygen vacancies in the lattice. Anyhow, this is for the oxide cases. But if you want to do that in other materials, there are various ways. In fact, this particular manuscript, which is kind of a review article, summarizes various ways one can create microstrain in the nanoscale material. Okay, it would certainly affect the electronic structure, and therefore your functional properties would change, and it may be very highly specific depending on the different approach you come across. Okay. Yeah, so what is the next question?
Yes, sir.
The XRD scan for 5 nanometer doesn't it show it shows, you see, the moment you are ordering is very small, the it's only for a few nanometers or so. XRD will always show a very broad spectra, very broad reflection peaks. Okay, X-ray reflection peaks. Whereas electron diffraction, you can get these things. Yes, it looks like more of amorphous space. Um, can you please tell us maximum band gap acceptable for different application area of nanostructures like 3.5 eV or I didn't get what is this question. Different applications means what? Which are, so for example, the solar cell I discussed, you need 1.5 eV, 1.5 to 1.7 eV. That's where you get maximum. The Shockley-Quasier limit basically suggests that maximum efficiency can be obtained when you have a band gap of around 1.5 eV. Okay, we can have materials which are larger, band gap can be used, but then the lot of sunlight, the energy that the photons that bring from the sunlight, a lot of energy will get wasted. Okay, it gets wasted as a thermal heat, and therefore it effectively does not convert the solar energy into useful electrical energy. But there are other applications where you need higher band gap. For example, I can give this TiO2 as an example, where it is used as a photocatalytic application, water splitting, and so on, where that particular band gap is very useful. Okay, so yeah, it is application dependent. Yeah, you cannot pretty much generalize it, but it's application dependent. Okay, so how do you calculate the number of layers in MOS2? Okay, so in the high resolution TM I showed, right? Should I share this? Let me once again share this. Can you see the slides? Yeah, for example, here you see this white to white is 0.64 nanometer, which is the distance between these two layers. Okay, 6.4 angstrom, and therefore you can count pretty much this one. How many layers there are? 1, 2, 3, 4, 5, 6. Like that, you count it, and you get the number of layers. If you want to do this same thing on thin films, monolayers and bilayers coated on substrates, then probably you may need to use a atomic force microscope. In fact, we did some study on that, which appears in Journal of Physical Chemistry C. These are all bilayer and tri-layers coated on silicon substrate. We have described all this thing in that particular work. Maybe you can take a look at it. Of course, this is but this is very pretty common. You can use an atomic force microscope and then find out the step size, and therefore you will come to know what is the number of layers that you have. But each layer is roughly about 6 to 6.4 angstroms. Are there any other questions?
Sir, we have one more question from our chat box. Can I share it now?
Yeah, please.
Yes, sir, the last one.
What is the efficiency of perovskite-based solar cell and BiFeO3 and double perovskite? Okay, so double perovskite, so far people have got close to 2% or something. But then a lot of research is still going on. Bismuth ferrite that we studied, we got 0.2%, which is of course 1/10 of the value. But then there are composite-based molecular beam epitaxy or PLD grown films of some other bismuth ferrite compositions, and those were shown to exhibit up to 8% of efficiency. Only thing is they did not do on a large scale, and if we can show that on a large scale, and that would be very interesting and very useful study. Okay. Yeah.
Sir, we have one more question from YouTube. Why major 2D material synthesize in oxygen deficient?
Why?
2D material synthesize in oxygen deficient.
2D materials synthesized in oxygen deficient medium, or 2D materials are oxygen deficient?
This is only given, sir.
Is it the oxide 2D materials you talk about, or most of the materials 2D materials are like the ones chalcogenide, or there are various kinds, but the oxide comes only the oxygen is more reactive. It can capture in case of molybdisulfate, for example, oxygen can replace sulfur and become MoO3. So not only deficient, sometimes it can become kind of a dopant and therefore alter the properties. I hope I got the question right. I don't know what he was asking. So
Sir, one more question. Can we use oxalate phosphate as energy conversion material?
Oxalates and phosphates?
Phosphates, yeah, as energy conversion material.
From what to what? Like which energy to which energy?
No, in general, I think they have posted, sir.
See, the phosphates, yes, we do use lithium ion phosphate, for example. Not all phosphates are very useful. Because for example, when it comes for lithium ion battery, the lithium shuttles in and out, and it has to be stable. When this lithium insertion and removal happens, the structure should be very stable, right? And if that is not stable, then there is no point in having that kind of material. So in spite of a large number of studies on the phosphates and other things, the only suitable material that they have found out is LiFePO4. Very good. There are very few materials that are suitable for lithium-ion battery application. Other things you will get voltage, but then in terms of the capacity, in terms of other required parameters, it may not serve the purpose.
Sir, how oxygen deficiency is beneficial for a particular application?
So oxygen deficiency is not always good, but certainly, as I showed in this example, the oxygen vacancies do impart certain properties, like it changes the ferroelectric properties, it changes the magnetic properties. I didn't discuss one particular work where we showed the magneto electric properties shows strong coupling between the magnetic and ferroelectric properties, and this is enabled by the oxygen vacancies. So in fact, if you want a very classic example, go back and see the yttrium barium copper oxide, one of the YbCO, as you may know, it's a superconductor. You need to have the oxygen in a right stoichiometry, and that delta is very important. And when you synthesize the YbCO, you have to control the oxygen flow such that you get the right composition. So oxygen in the lattice, in fact, plays a very important role, and the electronic structure depends on how it is, and a lot of properties, in fact, get affected. For example, if you take that indium oxide, you may know about the ITO substrates, indium tin oxide substrates, right? It's basically tin doped indium oxide structure, where the oxygen vacancies are the one which gives rise to large conduction, right? So yes, oxygen vacancy can be used, but it need not always be.
ப்ரொஃபசர் வந்து அவர் வந்து பேசிருக்கு, கேக்குதா உங்களுக்கு?
Yeah, it need not always be a beneficial thing, but there are large applications where it is beneficial. That's what I was trying to convey.
Yes, sir. Can carbon quantum dots used instead of metallic dots?
Where? Depending on where. For example,
in general,
see, carbon dots, again, they exhibit very special properties. Sometimes they're luminous also. So luminescent properties are there. So depending on what they want to use, the people are using it already. Yes. But not like metallic and things. Metallic nanoparticles are mostly used in catalytic application and so on. And so even carbon is used in some kind of a catalytic application. So it's application dependent, yes.
So any other question from participant side?
Dear participants, if you have any other questions, you can straight away ask to sir. You can unmute yourself to ask your questions.
So I think there is something I'm seeing here. So Pratima, oh yeah, this is a student from IIT Madras. So yeah, I remember her. So I'm glad to hear from you. It was interesting. Okay, so there's not a question. So just thank you, Pratima. How oxygen deficiency is beneficial for a particular application? That I think I answered all of that. Yeah, if you have any other questions, please let me know.
Sir, I have one doubt, sir. So basically, we have some porous type of materials. So in the case of porous type of materials, how one can engineer this type of defects so that we can enhance some properties like photovoltaic or photoconductive properties?
What porous material you have?
We can talk about silicon porous material or graphene.
See, the moment you, for example, you take silicon, see, it's highly material dependent. That's what I was always telling this. So for example, if you take silicon, and if you have a porous...
Sir, silicon in the form of single crystalline or multicrystalline.
Yeah, whatever. But in the porous form, if you have, immediately the pores will get filled. The silicon has a tendency to become silicon oxide. All these pores will have a coating of oxide layer, right? So that is going to affect the properties. So of course I mean, if you want to control the defect structure, you should take into account a lot of factors. The structural aspect, how what kind of defects you consider, how it affects the electronic structure, all these things you should take into account. And randomly we cannot talk about, I do have the structure, let me put it defects. I mean, the question is, it may be already be rich of defects, you are not aware of it because of the way you are preparing it. So the idea is identify those defects and then control them and show what we can benefit out of it. That's a bit challenging. Identifying the defects, the type of defects itself is a bit challenging.
Yes, sir. Thank you, sir. So I think there is no more question. So I think we can conclude our session.
Yeah, so thank you again, once again, for
Yes, sir.
this
I'll just
opportunity
conclude.
and interacting with all of you.
Yeah, sir. I'll conclude, sir. Now, thank you, one and all available here. So let me first of all start by giving glory to Almighty God for making today's occasion a grand success. Knowledge has a beginning but no end, and investment in knowledge pays the best interest. I thank our today's guest, Professor Sudhakar Chandar, for his wonderful presentation. Defect structure, correlation in oxides and chalcogenides, and its challenging factors in the point of material perspectives. It's interesting to know more about the insulating oxides from your interesting talk today, sir. Your talk taught us what is defect and how to identify the defect and how we can make it useful to certain properties. Increasing the defects increases the short current. And also you correlated the properties like ferroelectric and photovoltaic and photoconductive properties. The increase in oxygen deficient vacancy is always helpful in getting a desirable efficiency factor in the case of thin films. And also we come across the word of acoustic whispering gallery modes and optical whispering gallery modes and how it is effective in tuning the property of efficiency in the case of quantum dots as a mesoporous layer. So my heartfelt thanks to you, sir, once again. And I
Thank you.
also thank our management for their constant support and encouragement in all our efforts. I also thank our professor and head and all the staff members of Department of Physics for their constant support throughout this event. My heartfelt thanks to our participant friends who has joined from various institutions. I appreciate their thirst for search of knowledge nowadays. I also thank their constant support in our day 4 session. See, once again, thanks for all the participants and thank you for your patient listening. So thank you once again. Thank you, sir. Thank you so much for your
Thank you.
presence.
Have a good day. Thank you all.
Thank you, sir.
So
Thank you, sir. Thank you so much.
can I log out?
Yes, sir. Yes, sir. Thank you.
Okay, thank you. See you.
See you,
Yes,
sir.
sir. Thank you, sir.
Dear participants, we have few more minutes. Suppose you didn't fill your feedback form, you can take this time to fill your form. If it is not already filled, you can go for it now. Only 2 more minutes will be given.
Sir,
Yes.
sir, I attend the day 1 to day 4, sir,
Okay.
session, but I did not complete the feedback form, sir. Day 1 to day.
You please send
How
this
many day
message
from
through mail ID. Okay. The mail ID already given for You send this message
sir?
to mail ID, then I will reply for this. No problem, sir.
Okay, sir. Okay, thank you,
We
sir.
have your attendance in Zoom account, then no problem. We will verify that. We'll give you feedback form. No problem.
Okay, sir. Okay, sir. Thank you.
Dear participants, tomorrow we have session at 10:30 in the morning. So kindly please don't join the session. The session will be handled by Dr. KJ Shankaran, Senior Scientist, IMT, CSIR, Odisha. He is to deliver in CVD diamond thin films for optoelectronic applications. Please do keep up in mind the session tomorrow starts up in the morning at 10:30.
Dear participants, you please keep in this message in your mind always, okay? Because this is not of usual time. Tomorrow we have 10:30 session. That won't happen usual time. Usually we used to have 1:30 p.m. only. This will happen at 10:30 a.m.
Okay, sir. Okay.
Thank you. Anita, ma'am, can we finish it up? Okay, ma'am. Thank you.